Hello everyone, and welcome to today's webinar on variable refrigerant flow. We're going to get started very shortly, but before we do, I'm going to go over just a few webinar logistics. My name is Andrea Silvestri, and we have a great lineup today of speakers and presentations. So today's webinar will include an overview of a report by Pacific Northwest National Laboratory. And this report, the full report, as well as a 4-page findings and 1-page infographic are available at gsa.gov/GPG. And you can find additional resources here as well. Today's webinar is one in a series. We'll be taking a break in July and August and then return in September with a webinar on a recently released report on high-performing commercial rooftop units. This report evaluated the first advanced RTU to meet DOE's high-performance RTU challenge. October's webinar will feature a chemical-free treatment for process water and cooling towers. The report will be released shortly and shows very favorable results for both efficacy and water and chemical savings. November's webinar will present results from a soon-to-be-released assessment of LED fixtures with integrated advanced controls. Webinars are always hosted on Thursdays, and we'll be announcing exact dates shortly. All GPG webinars offer continuing education learning units through the American Institute of Architects. Today's webinar will offer 1.5 units, and to receive credit, you can complete the post-webinar survey that you should all receive just after the completion of the webinar. If you don't receive the survey, please contact Michael Hobson. Today's webinar is set to listen-only mode. And if you have questions, please submit them in the right-hand side of the chat box. And you don't need to wait to the Q&A session, which will occur at the very end of all the presentations. In fact, we encourage you to submit your questions well in advance of the Q&A. And with that, I'd like to turn it over to Mike Lowell, who will be facilitating today's webinar. Thanks, Mike.
Thank you, Andrea. Next slide. Welcome, everyone, and thank you for attending today's webinar. Here we have the agenda. Assuming Kevin is not here, first we'll have Andrea and I give a presentation to the Emerging Technologies, or an introduction to the Emerging Technologies program. After that, Ann will share the findings at PNNL around the VRF technology. And then we'll have a series of GSA people who will give us boots-on-the-ground feedback on the technology. Those people include David Johnson from Region 1 in Boston, Jason Silken from Region 8 in Denver, Robert Moctezuma from Region 9 in San Francisco, and then Joe Seufert from Region 10, which is in Seattle. After that, we'll have a Q&A session. Of course, as Andrea said, you can post your questions in the chat. We will then copy and paste those into a Google document, and we will go through those questions and address those at that time. With that, next slide. Next slide. I assume Kevin's not here yet. So Emerging Technologies consists of 2 sub-programs. We have the GSA Proving Ground, or GPG, and our Pilot to Portfolio program. The GPG program is the part of the program that basically has an intake. So every year we issue an RFI to the industry. People apply to the program, and we select technologies for testing and verification of their performance and produce performance reports on those technologies. That is the GPG program, the testing, verification, and production of results. Then we have a Pilot to Portfolio program, and frankly, our program is nothing or has accomplished nothing if we don't then deploy those proven technologies within our buildings. So that is the function of the Pilot to Portfolio program, is to get those proven technologies that we have tested and verified and get them into our buildings so we can improve our performance of the portfolio within GSA. Next slide.
And thanks, Mike. I'll jump in here and wanted to just give a perspective on why we're hearing so many multiple perspectives on VRF. So the first, when Ann Wagner from PNNL will be talking about technology review on guidance on where VRF is best suited. When PNNL completed their report in 2011, it was before GSA had any full-scale deployments of VRF to do measurement and verification on. So the report didn't include our standard M&V that we're doing at testbed locations. But since that time, we have GSA has multiple installations of VRF, and the cases that we'll be hearing from are representing different uses of VRF, kind of some of those places where VRF is best suited. So at the Moakley Courthouse, VRF was chosen for a need for simultaneous heating and cooling. So when there's challenges with tenant comfort, and you need different levels of heating and cooling, VRF was a good solution there. At the Wayne Aspinall Federal Building, this was a case where there was a historic building, and in the retrofit, there's limited room for ductwork changes, and so this is another case where VRF can be a good solution. The Bakersfield Courthouse installation in 2012 is VRF is used for separate data center spaces, and GSA has a number of installations of VRF used for these separate data center spaces. And then the Region 10 at the Vancouver Federal Building, this is another courthouse with the need for independent temperature control. So we're fortunate to get to hear so many kind of on-the-ground feedback of the installation of how VRF is working, and also this report and guidance from PNNL. And with that, I'd like to turn it over to Ann Wagner. Thank you, Ann.
Thank you. And that's enough of that one. We can go to the next slide. As Andrea mentioned, when GPG commissioned Pacific Northwest National Laboratory to evaluate VRF technology, GSA did not have a VRF implementation that was suitable for field study. Consequently, we performed our evaluation by examining available literature and talking with industry experts. The study primarily focused on the energy savings potential of existing buildings. I helped with this effort, and today I'll share some of the information from the 2012 study, as well as provide an overview of the technology. Next slide, please. According to 2012 CBEX data, about 44% of energy used by commercial buildings is used for space heating, cooling, and ventilation. Even though VRF systems are the primary type of heating and cooling systems in Europe, China, and Japan, a small portion of office buildings in the U.S. currently use this technology. You've probably heard this technology described in several ways. The technology was developed in the 1980s and designated as variable refrigerant volume, or VRV. But the abbreviation or term VRV is trademarked, so industry generally uses VRF to describe multi-split systems that use variable refrigerant control. Next slide. This graphic shows an example layout of a VRF system, providing independent temperature control to a variety of spaces. As you can see in the drawing, VRF systems are comprised of multiple indoor fan coil units connected by refrigerant piping to an outdoor unit. The outdoor unit has at least one variable capacity compressor. VRF is an all-electric technology, and there are three primary types of systems. The first type is the air conditioner, and this type of VRF system only provides cooling. The second type is the heat pump system. This type provides both cooling and heating, but it can only provide heat transfer in one direction at a time. So in other words, the whole system operates either in the cooling mode or in the heating mode. The third type of VRF system is the most efficient type, and it's the heat recovery system. Okay, we've got a screensaver, but that's okay. The system includes controls that allow simultaneous heating and cooling. Simultaneous heating and cooling systems afford substantial energy savings. And this picture illustrates how the system is able to remove heat from the blue spaces that need cooling and provide it to the pink spaces that require heating. When the heat is transferred this way, the compressor operates less, saving lots of energy. VRF systems control with precision. The flow of the refrigerant is varied to each of the indoor units to match the space requirements. And the outdoor unit includes an inverter-driven compressor. This combination of control gives these systems the ability to have a broad capacity range from as low as 10% to 100%. Next slide, please. One important aspect of VRF systems is that they are fully engineered systems. All of the equipment, including an integrated control system, is provided by the manufacturer. These systems are modular and have a limited number of components. They include, as you can see in the picture, some indoor fan coils, outdoor units, and a controller box. Each of these components are relatively small, so installation is relatively easy. In fact, an outdoor unit can be transported to a roof in a 6-person elevator. System designs vary among manufacturers. Some brands of VRF systems with heat recovery require 2 refrigerant pipes, and some use 3 pipes. Systems are designed specifically for each application, incorporating appropriate components and controls. All of the components are proprietary. Each manufacturer has its own unique components, controls, and piping configuration. One manufacturer system cannot be integrated with another's. Also, to ensure that VRF system performs as expected, all of the professionals, from the designers to the operators who are involved in the system implementation, must have received training from the system's manufacturer. Next slide, please. VRF systems are quite different from conventional systems in several ways. Here are some key differences. The first I'm showing I mentioned earlier, which is the broad capacity range of VRF systems from 10 to 100%, whereas conventional systems often can only turn down to 50%. Another significant difference is that conventional systems move heat through a building using water or air. VRF systems use refrigerant. Consequently, VRF systems use little to no ductwork. However, VRF systems do not include outside air. So either a completely separate outside air system is needed, or an outside air system needs to be integrated with the VRF system. Now, some renovations have taken advantage of existing ductwork and used it to provide outside air to spaces or to the indoor units. Next slide, please. Here's an exciting table from our study. So in 2012, in our study, we included this table. It shows a rough approximation of energy and energy cost savings potential across a portfolio of buildings in many climate locations. Our sources included 2 simulation studies as well as other studies. Now, if you look at the bottom 2 rows of the chart, they're kind of the heavy gray, you can see average savings from VRF systems compared to several types of conventional systems. The second row from the bottom shows average energy and cost savings from VRF compared to systems with electric heat. The bottom row provides the average savings comparing VRF systems with gas heat. Next slide, please. Here's another table from our study. It shows savings estimated for a range of GSA building EUIs. What we did is we looked at the average EUIs in GSA regions and were able to calculate the average portfolio EUI of 60.7. And you can see that on the top row under the column labeled average. We broke out the annual heating, cooling, and fan energy use from the overall building energy use, and this is shown in the next rows. Then we used a range of utility rates from GSA to estimate the HVAC energy cost savings from using VRF. The estimates were based on 34% reduction when compared with a chilled water VAV system with electric heat. Now, if you look at that green highlighted, it's 18 cents per square foot. This is the estimated cost savings for the average GSA EUI using the GSA average utility cost in 2012. Okay, next slide, please. Historic buildings can be very good candidates for VRF systems, especially if there's limited space to install or change systems. The primary feature of VRF is that they are less intrusive than other systems. Refrigerant lines are run instead of ductwork, and these require only small holes in walls and ceilings and need minimal clearance between floors. The indoor units can be located in the conditioned space, or they're units available with a low profile for installation above a ceiling. The smaller size of all the components lends to the ease of staging and installing the pieces of the system while minimizing disruption to a building. Frequently, historic buildings have a variety of separate spaces that need individualized comfort control. VRF systems are well suited for these applications. They precisely control the amount of refrigerant flowing to each indoor unit and can include many indoor units of differing capacities and configurations. There's also the bonus of providing simultaneous heating and cooling when the system includes heat recovery. This allows the transfer of heat from one zone to another and reduces the operation of the outdoor unit, saving energy. Next slide, please. An important consideration for the selection of a system is its cost effectiveness. And these two charts show number of years required for simple payback. The y-axis on both of the charts lists incremental cost. The columns show various energy cost savings values. The table on the left compares VRF systems to VAV systems that have hot water reheat and constant air volume systems with gas heat. The table on the right compares VRF to VAV systems with electric reheat. The service life of a VRF system was assumed to be 15 years. The cells with the white background show options with simple payback of 15 years or less, and the gray background designates simple paybacks of greater than 15 years. Next slide, please. There are barriers to implementation. The complete VRF system must be provided by just one manufacturer. This requires combining the design with the installation and commissioning of a system. This approach conflicts with the design, bid, build, procurement approach. Currently, GSA's procurement process begins with the design. Then the project is put out for competitive bidding. However, a proprietary design and integrated implementation approach for a VRF system creates a hurdle to getting competitive bids from other manufacturers' systems. Another barrier is first costs. Initial costs of VRF systems are often more than conventional options. However, there are cases where costs may be similar or less. This can occur when there are substantial space constraints or challenges to alternative system installations, such as installing ductwork or increasing weight-bearing capacity to a structure. Also, incremental cost and life cycle costs should be considered to better compare what lifetime total costs will be. A third barrier is uncertainty of savings. There are not many cases documenting the savings realized by VRF systems. Also, there are three types of systems, so care must be taken when examining savings documentation. There are AHR ratings now, and these provide verification of equipment performance at certain conditions. Next slide, please. Where to apply VRF? It says not one size fits all, but there are many opportunities to use VRF systems. Some applications are stronger candidates than others. Merits of VRF systems include energy savings, ease of installation, integrated controls, and comfort. Potential project characteristics may include the need to upgrade the HVAC system or to add cooling. Project space constraints, such as limited room for ductwork, minimal clearance, or minimal space for equipment, can be reasons to consider VRF. Projects that have multiple separate spaces with various heating and cooling needs that would benefit from precise, independent temperature control are also good candidates for VRF. Buildings with electric heat are good candidates because both the heat pump and heat recovery systems are more efficient than resistance heating. If the building can take advantage of the heat recovery offered by a simultaneous heating and cooling system, then this type of VRF can help you achieve your energy reduction goals. Our study determined that there are opportunities for GSA buildings to benefit from VRF technology, and that the best building square footage range for GSA is between 5,000 and 100,000 square feet. There's no quick answer to the question, where is the best place to use this technology? But as you've heard, there are a lot of things to take into account when determining if a VRF system is the best choice for your project. Now I'll turn the webinar over to David Johnson, and he'll present on GSA's experience with the system installation at the Moakley Courthouse. Thank you.
Thank you, Ann. Good morning, everybody from Boston, Massachusetts, Region 1, New England. So Region 1 installed a VRF system at our Moakley Courthouse, which is our large federal courthouse in the Seaport District of Boston, Massachusetts. So a little bit about the Moakley. It's just shy of 1 million square feet. It is a federal courthouse, 10 stories. And this was an hour project that we did and evaluated it in 2009 with the retro commissioning, and we were looking at a simple payback of about 6 years after that commissioning report. We had planned to do the 9th and 10th floors of the Moakley, but due to installation costs, mostly driven by the need of the courts to have this work done after hours, we actually ended up only doing a partial install on the 10th floor, basically 17 out of 26 phases, which was about half the 9th and 10th floors. And we completed this project in 2011. So for those of you who want to know a little bit more about how that played out, we completed the design in April of 2010, and were able to give the construction notice proceed in July of 2010. Construction started in March, and we completed those phases in the course of several months. So it was a detailed project, but a little bit about the VRF system. Next slide, please. We did end up using a water-cooled instead of air-cooled system there at the Moakley. The reason we selected that was there are a few security concerns from the marshals and the courts, mostly the roof openings that we would have had. It was a little bit easier for our O&M to access the equipment and provide that corrosion due to marine conditions. If you saw the photo there, the Moakley Courthouse is on a pier out into Boston Harbor. So, and then when we looked at the finances and the payback, it had a slightly better payback to do that. So we ended up using existing cooling towers and an existing heating plant to give both heat rejection and to give the system heat. It also allowed us to use a refrigerant pressure differential on the high-low at the cooling units for leak detection rather than the occupied space leak detection required by ASHRAE 15. A little bit on the maintenance side, because looking at operational excellence, we replaced some washable filters with MERV 8 filters, and our boxes there came with a liner for sound. Next slide, please. So how did we know? We installed it, and the installation, like I said, was after hours, and we would return the spaces to occupancy during the day. Which, for those of you who work with courts, know that is a tricky process, but it was very successful for us. But how has it worked out since we installed it back in 2011? Well, like many of you in the field, no news is good news, and we do not hear a lot about the VRF system at the Moakley, which is for us a great success. When we look at the system, we see that we've had a 12% reduction in overall utility spend. To be upfront about that, that does include other upgrades such as BAS and lighting, and since this did not have the type of, as spoken about earlier, we didn't do full M&D on this as it was a era upgrade and not so much a straight up GPG project like some of the other ones. A portion of that is for the VRF system. But when we say no news is good news, we mean both from the building operators, being the GSA property management staff and our O&M contractor there, but also the tenants have no complaints as well, so that is always a good thing. It's been spoken to, and I see some of the questions in chat. Yes, we did find that using the proprietary controls that come packaged with the unit was actually very good for the install. But we do have supervisory of that linked into our BAS. So there is a question about, do you have package controls on your chiller system that are packaged to the chiller system, but then talk back to your BAS, and your BAS monitors that system. And that is exactly what we use there at the Moakley. We did, as far as how robust was the install, we did have a unit go down, but that unit was replaced by Mitsubishi, and they were very responsive to our issues. So we do know that there is some feedback from across the nation that some people will get into later about how widespread is support for this and how do these systems get supported because they're relatively new to the U.S. market. But we have had good results with the manufacturer being responsive to any issues that we do have with the system. Next slide, please. So as far as lessons learned, yeah, using that that manufacturer's control interface was a lessons learned. The BAS does only have control and monitoring of that system, of that subsystem. And performing that site verification during design to make sure there's sufficient physical space for those units was also an important lesson learned. A few other things that we did to make that really work out is that we did send the O&M to a multiple day offsite. We found it was important because our O&M contractor was not familiar with how a VRF system would work and how to maintain it. So it was, for us, it made good sense to go ahead and spend that money, and we actually got 6 of the contractor's O&M staff through training. And I think that that was a good lessons learned and something that we would like to replicate in other and further projects. Next slide, please. And really to conclude is that they have an obvious energy efficiency, and we do use them for simultaneous heating and cooling, not to miss that point, but the courthouse, because of the type of occupancy it is, it actually has a need to heat one space while cooling another, so we're able to use that inherent simultaneous heating and cooling situation that a VRF gives us to drop our energy costs. At the same time, it actually makes the zones more comfortable for our tenants, so there's a good payoff there. Our units are very quiet. They have a quiet operation. And it's actually fairly low maintenance. They really just change the filters and clean the coils on them. For safety in a courthouse, we're not recirculating air from one zone to another, which there are some concerns about in a courthouse for airborne contaminants and allergens. And the flexibility that we gained, especially the flexibility during this install, was able to go zone to zone and do in-zone while the rest of our building remained in operations. It was really quite a sight to see, and we have quite a bit of photos that we could share at another time of how we did that, and were able to return a space to full operation for a client like the U.S. Attorney's Office or the U.S. Marshals during an overnight, and they had full operation of the space during the day. So that is very positive for us. So would we do it again is always the other question, and the answer to that is yes. We're doing additional VRF installations right now that we probably will talk about in a further presentation, but we got one going in at a border station right now. So that's what we do. What I'd like to do is that concludes the Moakley's presentation, but from Region 1. But I'd like to turn this over to Jason Silkin and Roger Chang from Region 8 because they're going to talk about another courthouse that they've done out there. So Jason and Roger.
And before Jason and Roger, before you get started, we're hearing some feedback from a line, and I'm not able to mute it. It's an area code 419, and it ends 5080. So we're hearing feedback from your phone. If you could mute your line. Thank you. And thanks, Jason and Roger, now.
Great. Well, thank you. So I'm Jason Silkin. I'm a architect and project manager from GSA Region 8, and I'm here with Roger Chang.
Hi, I'm Roger Chang. I was an engineering leader on this project with the LR Group.
So next slide. So to provide a little bit of context to this install, the Wayne Aspinall Federal Building and U.S. Courthouse, that's located in Grand Junction, Colorado. Grand Junction is a smaller community on the western slope of the state, and it's in a relatively dry and arid climate. The building itself was constructed in 1918. It's on the National Register of Historic Places. It's a small building, a little over 41,000 gross square feet. It's 3 stories above grade. However, it houses 9 federal agencies, including a fully functioning district courthouse. The modernization here was funded by the Recovery Act. We awarded this as a design-build contract in 2010 to Roger's team. Construction was completed in 2013, and in September of 2014, we completed about an 18-month performance verification and M&V period to dial all of the building systems in. The project scope was a top-to-bottom modernization of the building. We are replacing all of the major systems in the building, many of which were failing at the time. On the flip side, we are also restacking the building to kind of create a more efficient layout, improving our RSF. But in addition, that allowed us to preserve and restore significant aspects of the building's interior that had been lost through previous renovations. And you can kind of see that on those 2 photos to the left, the pre-project conditions. This kind of overall approach to this building, or scope of this project, rather, gave us an opportunity to really kind of approach this as a whole building design. And since this wasn't our project, the end product was required to be a high-performing building. And since this was a historic structure, the modernization really needed to support a large preservation effort. And so at award, our performance goals on the design-build contract really kind of evolved beyond our minimum performance criteria, but included stretch goals such as LEED Platinum and net zero energy for this project. The reason I feel this backstory is important is all of these factors kind of created the metrics Roger and his team used for system consideration on this project. Next slide. So working with our construction manager, Jacobs, at the RFP stage for the design-build contract, they created a performance spec which offered up systems for consideration, kind of beginning with a baseline, followed by improvements to the baseline that we felt could better meet our overall goals to this project. And so that really kind of created 6 metrics that we were looking for in terms of system consideration. Footprint, as that related to our preservation goals, we wanted something that was slim and could allow us to reestablish those original volumes in the building's interior. Efficiency for our energy and sustainability goals. Zoning, considering the number of agencies we have in the building as well as their orientation on the floor plates. Zoning was a major consideration on this. IEQ, both for ARA and LEED. Response time, we had agencies like the U.S. District Courts and the IRS who would see a large influx of visitors in a very short period. And lastly, complexity. We needed a system which could be managed by the O&M in the building and also be able to be maintained locally, knowing where Grand Junction sat between the closest major city, which was about 300 to 400 miles away. So I'll turn it over to Roger to talk about how his team sort of evaluated these systems.
Well, thank you, Jason, and thanks everyone for allowing us to be on this webinar. So we used energy modeling to look at the variety of systems that Jason showed on the screen, even from the pre-award phase. We're looking at what provide best value to GSA to select. The radiant cooling and heating system actually came in a close second to the system. The VRF system had the best overall life cycle cost out of all the systems considered. But really, one of the biggest drivers is just its ability to be fit within this historic building from the early 1900s. The variety of fan cool units that are available with a VRF system provide significant zoning flexibility, a good acoustic footprint, and also address this desire to have very short warm-up or cool-down times due to the variety of schedules used by the different tenant agencies in the building. We ended up choosing a water source VRF system. This was a measure in order to drive the energy use intensity target achievable down further in order to balance with the limitations to how much on-site renewable energy could be provided for the net zero energy goal of this project. We ended up with 6 twin sets of water source condensing units. You can see these installed on the left side of the picture on the screen, and each set had between 12 to 20 tons of nominal capacity. On the indoor fan cool unit side, we primarily used ducted low-profile ceiling-mounted units. These were installed with relatively short amounts of supplied ductwork and provided with ventilation air from a separate rooftop-mounted dedicated outside air system. That dedicated outside air system did have additional zone-level control with the VAV single duct boxes in the quantities that you see on the screen. Refrigerant piping was brazed copper in a 2-pipe configuration with 10 branch controllers, each with 8 to 16 nodes. Next slide. So just some general initial observations. As has been mentioned, for every manufacturer, we are dealing with very proprietary technology, and so we are operating these in somewhat of a black box condition. So unlike a traditional air side or hydronic system where you can measure temperatures and flows and do an energy balance to see how it's performing in relation to electricity or natural gas input, is actually much more difficult to do with a VRF system. And so one of the things that we were challenged with during the M&V period of this project is to say, do the results actually match the model results? And if there is a deviation, is it because of the way the system is installed, or is it because of operating conditions, or is it because of some limitation in modeling software? So it's one thing that we had to consider in the post-occupancy stage. Although variable is in the title of variable refrigerant flow as a system, the operation is not a continuously variable modulation, but rather is actually in steps. The water source heat pumps we use each have 12 steps of control. As has been mentioned, controls integration can be challenging, especially if you want to do some integration with a building automation system through an open protocol. In this particular case, our biggest challenge was actually doing subpoint scheduling for each tenant agency by time of year and also linked to outdoor conditions. Eventually, we were able to integrate to the needs that we wanted, but it did take quite some time in order to particularly have subpoint limitations. So for example, during cooling, being between 75 to 78, for heating between 69 and 72, initially we had to have a wider range in the installation. The system really is optimized for standalone control. So when these are installed, we're just using a wall-mounted thermostats and maybe a manufacturer-provided touchscreen panel. They work very well, and they tend to be fairly easy to commission. It is, again, when you're using that building automation system, that doing everything you want it to do can be challenging. Just the data on the right is just our energy use intensity for the building. We originally had a target of around 15 for energy use intensity. After observing actual process energy use from the different agencies, this was adjusted up to approximately 20 in the building in its first year after some systems optimization operated close to that target, and after considering the contribution of renewable energy, operated close to 6 for a EUI, so significantly less than a median courthouse office building for this climate zone. Next slide. One thing we found is that there is really no benefit to twinning in this particular application for a water source application, unlike a system that might have 2 compressors. In this type of condition with this manufacturer, if one compressor fails, actually the entire unit goes down. One other thing we observed is the AHRI rating process. While it does allow for comparison from one system to another between different manufacturers, it doesn't have a rating condition below 25% as a testing point. This particular building had a lot of conditions of operation where we're under very low demand, where the system doesn't necessarily perform as efficiently. Overall, it performs efficiently, but may not turn down as well as one might anticipate. Our sizing in retrospect was more conservative than needed in terms of applying some of GSA's standard guidelines for process load. This building ended up being a heavily process load managed building, operating down as low as 0.1 watts per square foot at night and about 0.2 during the day. And so there was the ability to potentially apply more diversity in the design sizing. As has been mentioned, energy modeling, there are not very many tools that can natively model these systems. And D-ratings do need to be taken into account for actual installed pipe length, the fittings, the altitude of the installation, and also defrost oil return cycles that can temporarily interrupt performance. The graph that you see on the right is actual annual electric demand for the building. Pre-modernization, just the installed lighting power density for this building was 2 watts per square foot. Post-renovation, the whole building was able to operate under 2 watts per square foot, with the VRF system contributing approximately 35% to the energy use of the building overall, with a 1-hour electric peak of approximately 1.2 watts per square foot. So a very, very efficient system. Next slide.
And Roger, we're getting some feedback that it's a little hard to hear you, so if you want to speak up or move your microphone, that would be helpful.
Oh, sure. So just some considerations for future use. We did end up using a 2-pipe system on this project, while 3-pipe is common to most other vendors other than Mitsubishi. There is potentially higher efficiency potential when you're really utilizing the heat recovery application for these systems with a 3-pipe configuration. One thing we did realize on this project that's very interesting in working with the manufacturer is that because there is still a separate condenser water loop, in this particular case it was tied to a ground source heat exchanger in a parking lot adjacent to the building. That is a component that is not directly controlled by the VRF control system. In that case, it's controlled by the building automation system. So there's a potential for some integration challenges with how those two react to each other, while when using an air source system, all of the controls are completely packaged, integrated together, and optimized by the particular vendor. So in this particular case, we were trying to do full variable condenser water flow, and actually found that the manufacturer had a limitation, actually an error in their documentation about what was possible. And for this project, they ended up making revisions to future product lines based on some of the observations from this project. Filter change, whether with a VRF system or any sort of fan coil unit or fan-powered system, is a consideration. In this project, we had over 60 distributed fan coil units. So we use care to make sure we address how those filters are changed, but there is still that decentralized component that needs to be taken into account. Water source systems, we believe, even in one more generation past what we use for this project, can actually perform with better variable condenser water flow. It is a very complex refrigeration cycle that requires that controls package that's provided can react to that complication or complexity. Next slide. And just the last slide here, it was important to plan commissioning and MV as early as possible in this process to understand how the data that's collected will be used to further optimize performance. One thing we observed for this project, not only with this equipment type, but other equipment on the project, is just that equipment standby energy performance is not always available, but for an ultra-low energy, high-performance energy building target, every bit counts, and sometimes even just parasitic control panel energy can really add up. For this system, we found just a continuous 300-watt controlled power demand. That adds up for a building that's trying to target a 15 for energy use intensity. As we saw, there were some challenges with controls integration for subpoint control. We had to tighten that several months after occupancy, and some tenants were initially taken off guard when they could have a wider range and it was narrow later on. So it's important to get players from the manufacturer and the controls vendor in as early as possible so that can be set up as early as possible. This last image on the bottom just shows an electric demand profile for one of the twinned sets, and you can see some of the modulation that occurs over a 24-hour period. The blue versus yellow, red shows compressor A versus B cycling and flip-flopping. So thank you for your attention and questions on this particular project. I'm pleased next to introduce Robert Moctezuma, who will talk about a project in Region 9.
Yes, good morning, everybody. My name is Robert Moctezuma from Region 9. I'm Building Management Specialist in the Central California Field Office. The Bakersfield Federal Courthouse is part of our inventory in Bakersfield. The next slide, please. So the Bakersfield Courthouse was constructed in 2011. It's a relatively small building as far as our inventory goes. In our use for VRF, it's used only for 4 dedicated server and equipment rooms dispersed throughout the building, totaling only about 400 square feet in total. Has a master and slave air-cooled heat pump outdoor units on the roof and 4 terminal boxes dispersed throughout the building. It's a 2-pipe system design, and it's only used for cooling and is operational 24/7. The remaining space is conditioned by an air-cooled chiller in combination with an active beam system and only 1 air handling unit for the rest of the building. The next slide, please. So the benefits of the Bakersfield VRF installation have been due to the dispersed location of the server room / equipment rooms that it serves throughout the building, some on the first floor, some on the second floor. It would be the runs for piping for a traditional system would be not a possibility in this location. One outdoor unit serves 4 different agencies: the U.S. Marshals Service, a couple of the bankruptcy and trustees, server rooms, security equipment rooms. Some level of redundancy. We experienced an outage of the slave unit, but due to the fact that these units are twinned together, the master was able to continue running, obviously at a reduced cooling capacity, but we were able to maintain continuous operations for our tenants. It's more efficient than a standard system due to the high turn-down capability of 20 to 100%. The next slide, please. We have had to make some repairs to the system. We've experienced, as others have mentioned, a little bit of a black box situation. Limited access to troubleshooting and repair information for non-factory certified personnel. Along with that, I know that folks that were originally part of the project, the operations and maintenance team, we do periodically have turnover in our operations and maintenance contractors. So training of those contractors and the follow-on contractors, when the operations and maintenance contractor changes, that's definitely a consideration. Weaknesses in the system have been electronic in nature. So again, we kind of get into a black box area where it's not traditional, refrigerant and electromechanical components that we're experiencing trouble with. In that sense, the units have been very reliable and relatively trouble-free. The experiences that we've had has been faults in serial communications between the master and the slave unit, and it really drives us into a corner where we are almost forced to rely on the manufacturer to provide us that technical support. Again, limited VAS integration. The manufacturer in this case is Dakin. They do have a backnet interface that does allow us to see, temperature, set points, operational status, and whatnot. So it's not completely standalone in that sense. Next slide, please. Okay, so with that, I'll turn it over to Joe Seifert for Region 10.
Good morning, this is Joe Seifert. Region 10, I was the mechanical engineer reviewing these design drawings and then actually going down to do a quick commissioning of this installation because we didn't have commissioning involved. Next slide, please. So some of the issues that I've seen with this installation and others prior to joining the agency, we talked about the limited visibility into the BAS and the black box that both Robert and Roger had talked about in depth, so I won't go into it. It makes it tricky when you try to do any sort of commissioning, of course, trying to see what's into the system. You really just have you're giving a set point and maybe you're having an alarm coming back, but other than that, you can't really interrogate the system very much. Condensate with these systems, so they're either gravity or they're pumped from the unit itself, from the cassette. I've seen both. This installation was a pump installation, so you have alarms associated with the pump within the cassette unit, but then it's then going to be pumped. In this installation, they pumped it to another booster pump, if you will, condensate booster pump, which is not on the BMS. So we didn't know whether we had a failure of that booster pump for the condensate, and it overflowed into our courtroom area because we didn't know it was an issue. So so there's issues with condensate. You have to insulate it if you're going to have humid conditions. So there's just concerns associated with the condensate that it's done correctly. And if it's gravity and there's no pump at the unit, we've got to make sure we individually trap those units so that they can drain properly. So that's condensate. Refrigerant, we got to make sure we're compliant with ASHRAE 1534 in terms of the amount of refrigerant we have in the space. That's up to the designer to make sure they adhere to, but it's also up to the contractor to make sure they put the proper refrigerant in. We got to make sure we properly insulate those lines because, again, we're going to sweat above the ceiling. We've got some pictures of that not working the way it's supposed to. And I think others have talked about the training. We've got another installation at Anchorage where they don't know how to operate it. So that's key. Next slide, please. So here's some examples of poor refrigerant installation. So that vapor barrier isn't sealed, so you have an opportunity to sweat. It was just not done well. So on the right is the cassette unit itself. On the left, I believe, is the branch controller. So lots of opportunities for sweating above the space. And if you look at it, they actually use a flexible refrigerant line, which really, it could be like spaghetti going through the space. It was a little concerning. It wasn't they weren't nice clean lines. So there was opportunity for us to, it was good for installation, easy installation, but in terms of trying to make sure we know where those lines are and we don't hit them in the future, it's a bit of a concern. Next slide, please. So we talked about the condensate. So one thing that I've seen in several locations is the use of PVC on the condensate. So on the left-hand side, it's a poorly supported PVC, which then they would replace with the copper on the right-hand side. So notice what on the right-hand side, this is the booster pump. So it's going to be pumped into this reservoir for the booster, and it's not sealed. You can see there's a little annulus there. So when it overflows, it's just going to flow right out and spill into the courtroom, which it did. And that little booster pump wasn't on the BMS. It's still not. So it's a lack of communication in terms of what we should be doing to properly monitor our system. Next slide, please. So the actual Vancouver installation itself, so this is in Portland, Oregon. So it's a mild climate. I saw one of the questions, but it does have 90+ degree days for several days during the summer. So it does have both a heating and a cooling load, and that's really important. To echo what Anna said earlier, this is a small installation, but in order to get simultaneous heating and cooling, in my opinion, you need to look at a whole floor installation or a whole building installation so you get the opportunity. This we did not. So it's only 5,000 square foot out of the 20,000, 20-some. It's about 20% of the building on the second floor, two-story building. It's got the occupancy is courts, bankruptcy, so there's some courtrooms, and then there's other spaces, so IRS. And what was happening here is we were freezing out the IRS because we were trying to make it colder for the courtrooms. So they just wanted another system, and that's what this was, so that they had independent control in the courtrooms. So I think it's a 3-zone system, pretty straightforward. Really no opportunity for simultaneous heating and cooling. It's meeting a need. So next slide, please. Of course, additional ductwork wasn't needed, and one of the main benefits, with the exception of the outside air. And on this system, incidentally, so if you're not doing a whole building, you don't have a real good opportunity for a dedicated DOAS system. So you can't minimize your penetrations through the roof. This system used 2 Losnay ERVs, so you had multiple penetrations through the roof, which really made the system quite complicated. So we didn't see an efficiency improvement on this building. The tenants aren't happy, though. I mean, they're happy with the system because they got a standalone system just for the courtroom. So they were going to be happy whether we went with VAV or any system. And we're not overcooling the other floors that were on this. It's quiet, although we did do a sound test, and the sound test showed that it was going to be louder than what the U.S. courts would allow, but they haven't complained yet. So, and part of that could be, there's a low, medium, high setting on these cassettes. So you're cycling through those settings. So as an occupant sitting in the space, you're listening to this cycle, and it may not be loud, but it's different. It's not something you're used to hearing. Mostly used for cooling, yep, because you've got a high occupancy load for the courts. Next slide, please. So here's a BAS automated logic screenshot. So you've got all kinds of feedback within the system. We've limited tie into the BAS, limit control. We talked about that. Next slide, please. So lessons learned. The exhaust and the intake. So we've got a P100 requirement that says you've got to have a 15-foot separation between the exhaust and the intake. So when I walked up there, they didn't have this on the drawings, incidentally, or we would have pointed it out early on. So there's like 3 or 4 feet separation between those two. It's a Losnay. It's not a dedicated DOAS system. If it were for the whole building, we'd have a better opportunity to provide that separation. But instead, we've got these 2 little independent controls. And incidentally, there are 2 penetrations here, exhaust, outside air. And then for the other Losnay, there's another exhaust and outside air. So there's 4 penetrations for just this little 5,000 square foot area. So in terms of your penetrations to the roof and mitigating water damage in the future, this is not the best solution. But they weren't far enough apart. We had a debate as far as whether they needed any separation at all. If you look in the DOAS ASHRAE book, it talks about a minimum of 10 feet, which is the mechanical code requirement. They argued it wasn't an exhaust, but I don't agree with that. So yeah, so we talked about the condensate drains. One of the issues we had in the building was because we were able to disconnect the old system, they didn't properly disconnect it completely. They just used the OBDs, and air bled by, and you could hear it. So you got to actually cap the ductwork. Next slide, please. Where's my slide? Oh, okay. So VRF recommendations. So no VRF design guide is one thing I'm going to throw out. So I can turn to my ASHRAE systems and equipment book, chapter 18, and you've got some guidance in the ASHRAE handbook, but there is no book that I can pull off the shelf that provides you the design guidance or install guidance. For example, there's a nice OAS ASHRAE book that folks can reference. There's a nice chilled beam reference guide, and there's a reference for USAD. So there's lots of guides out there that ASHRAE has produced, that technical folks have produced, but there's limited information about VRF systems. And I think that's something that the industry is having a problem with. So we've got to make sure that we get the right contractors that have installed this before, the right designers that have designed this before. That is not what we got in this project. As-built records. Sure, maintaining as-built as we go forward, understanding the limitations. So my experience is I've done some previous ones with Camp Lejeune. There are other examples where people have been using VRF longer than we have that maybe we want to reach out to and see what some of the issues are. And I wanted to stress the use of simultaneous heating and cooling. We have it on this application, but we don't really have enough various zones that we can use it. So it was kind of a missed opportunity. Some things that we still have outstanding. There's some scanning issues associated with the IT equipment. We're still not over that. So that's a concern. You have to go into it, making sure your folks are involved. I would always recommend commissioning so that we're properly commissioning this at the end of the system. And there are some cold weather concerns that if you're going to use this in the cold, that you get low ambient kits and your height of your unit is high enough on the roof. So you got to make sure that you're properly doing it. Also with the DOAS system, if you don't have a dedicated DOAS and you're just using a LOSNE, there are filtration issues. They can only do a MERV 7 or an 8, so you won't give your MERV 13 that you're going to need for this for this courtroom type building. So that's what I have, and I'm going to turn it over and mute myself.
Hi, can you hear me?
Hi, we can hear you now. Thanks, Mike.
Okay. Welcome, everyone. Thank you. Just an FYI, we received so many questions that we're not going to be able to address all of the questions for the Q&A session. So we're going to be focusing upon those questions that appear to be kind of more global for the presentation. So with that, let me get started. Jim asked, are there any VRF systems coming to the market which do not have proprietary controls? Currently, the UFC, which is applicable to all DoD projects, requires that VRF systems have open source controls compatible with LawnWorks or BACnet. I don't know if Ann or anyone knows the answer to that question.
This is Joe. I mean, they may be compatible with other systems, but it's not like we're going to be able to plug and play, an LG unit with a Mitsubishi unit. They're still going to have to stay within that with that manufacturer's framework.
Okay, thanks. Ed asked, what is done to deal with the potential release of refrigerant within an occupied space? How does one deal with the required venting of that material? Anyone have a thought on that?
So this is Joe. If you're going to design it for 15 and 34 ASHRAE compliance, which just says the size of the room and the amount of refrigerant, if you have a leak, you don't necessarily have a detector that says you have a leak. And you don't necessarily ventilate. That's not how those systems are designed like that.
Okay, thank you. And Demetrius asks, how do you deal with the Buy America Act? Are there enough systems within the U.S. or within our trading partners? We're having issues with getting them approved for the Army.
So this is Joe. We did a waiver in Vancouver. You have to do a specific waiver because there is no one that meets the U.S. requirement.
Let's see. Winston asked, how is the refrigerant line condensation controlled above the unconditioned ceiling grid? Joe, I know you had, it's the insulation, but any other thoughts on that?
So making sure that we have insulation to start with, and then it's continuous. So we have a continuous vapor barrier. So if anything is going to sweat, that's going to sweat certainly before the condensate lines. But as I showed in my photos, it's not completely sealed if you've got a contractor that's not checking things. So it's certainly an opportunity that we need to be looking at from our perspective to make sure quality control and quality assurance is met.
Okay, thanks. And then Jack asks, And so Ann, this is a question for you. I understand that Mike Rosenberg there at PNNL has done some research that shows that in the Northwest climate, the heat recovery function of VRF is seldom cost effective or even used much. Do you have anything that you could add to that or respond to that?
Oh, sorry, I was on mute. I'm not really conversant on what Mike's done, but I do know in the Pacific Northwest there have been quite a few systems installed in Portland area, and I know of quite a few that have been installed, completely engineered, designed, including coupling with DOAS systems and other high-performance equipment that have been very efficient. There are some case studies, I believe New Buildings Institute did one on the Mercy Corps that have been found to be very effective. Again, as I said earlier, one size doesn't fit all. Depends on if you do have the opportunity to have simultaneous heating and cooling. A lot of buildings here don't. We have a lot of buildings that use outside air for cooling. So we have low levels of hours of operation of pressurized systems. We also have facilities that don't have much of a heating load. And if you have electric resistance heat, DPA has done quite a bit of studying on the systems and have found them to be very successful in a lot of their territory when the only heat available is electric resistance. So they've replaced electric resistance systems with the VRFs, whether they're the heat pump or the heat recovery that are even more efficient. So it, again, depends on the application. It doesn't fit everything, but the benefits of the partial load, being able to turn down the system to very low loads is beneficial, can be very beneficial for certain applications, as well as the ability to recover heat with the heat recovery system and find greater savings. So as with many parts of the country, different buildings, different needs. In the Pacific Northwest, we have some excellent applications and some actual case studies available. And then there's some locations that would not be, or some applications that would not be the best. So, as I said, not familiar with exactly what Mike's been looking at, and now I'm going to check into that since he is one of my colleagues. Thank you, Jack.
Thanks, Ann. And then Winston asks, are there any refrigerant leak sensors in the systems that we described today? I know that Joe said you didn't have any, but are any of the other presentation teams aware of leak detection systems in your installations?
Not on the Aspinall project either, no.
Okay, I'm going to take silence as no. Jack asks, it seems like smaller VRF systems are more efficient than larger VRF systems. What do you think about using perhaps multiple smaller VRF systems to serve a single larger building?
This is Joe. That's how they're designed. So they have multiple outdoor units, and they stage up from that. So it's not a really large outdoor unit. It's several smaller units. So on this little project that we did for 5,000 square feet, we just had one outdoor unit. But on larger projects, you're going to have multiples of those, and those are added on as needed for the load.
Okay, thanks. And then Jim asks, in climates where heat recovery function is seldom used, would non-VRF heat pumps be a better option? And Roger typed in, yes, there's less refrigerant piping complexity and equipment cost if heat pump only systems are used.
Yeah, and I just want to add more that maybe relates to this as well as the previous question. What's really key for these systems is just to understand the load profiles of all the zones that are attached to a single condensing unit. So you want to exercise the full range of potential with that condensing unit. And if you have just more of a fixed load, you may not really need to use VRF technology. You might use some other just single condensing unit to a space type of arrangement. So it's definitely dependent on each individual scenario, but definitely understanding the load profile will help drive some of the actual design.
Okay, thanks, Roger. And then Mark asks, and its assumption, can you provide the O&M cost increase for maintaining and repairing a large number of VRF units located in difficult to access locations above ceilings versus a small number of traditional air handler units located in easily accessible mechanical rooms? So I guess the question is did any of you see an increase in cost, and was it for those reasons, lack of accessibility, et cetera? Or do you face that issue?
On the Aspinall project, I don't believe that was an issue post-construction. I think just kind of going back and making sure your building is the right fit for this type of application. The Aspinall project is a smaller building, under 50,000 square feet, and so that kind of maintenance and filter change on those units was relatively manageable for the O&M there. I could see how that could be problematic on much larger facilities.
Okay, thanks. And then John asks, you did the derating for piping and altitude in the energy model, question mark. Are you talking about pipe losses from the refrigerant flow? What program did you use to model that? So this would be, I think, specific to the Aspinall. Roger says, oh, go ahead, Roger.
I was just going to say, so manufacturers, when they actually give you a submittal for a particular configuration of outdoor unit and fan coil unit, they do account for the refrigerant piping length in the actual peak energy consumption, heating and cooling. They'll also do that derating for the design ambient conditions. That data can then be used in maybe a wider variety of energy modeling tools, whether it's an eQuest or Energy Pro or Train Trace, which are commonly used. Right now, to my knowledge, Energy Plus as a simulation engine is the only engine that can natively model refrigerant piping length, impact of fittings, impact of installation elevation, kind of more of secondary or tertiary factors in impacting efficiency. While most of the time the industry is using more aggregate information and empirical models to do the modeling. So Energy Plus, if you know how to use that module, you can get a more precise simulation. But right now, there are still some approximations that occur.
Okay, thank you, Roger. Thomas asks, we've got a number of outdoor VRF control board unit failures. Should any special consideration be added for these VRF installations given those failures? I guess it's all about dependability is the question. Any thoughts on that?
This is Roger. This may just be looking at who has the best service presence in a particular region where a building is located. I think if you looked at market share for the different manufacturers, I don't want to talk about any particular manufacturer, but I think there's two that are a bit larger in the United States right now than the rest. I've heard that there's been, I think, overall better experiences with those two big companies.
Roger, this is Joe. Could we ask who, in your opinion, those two are?
Sure, Mitsubishi and Daikin.
Thank you.
Thanks, Roger. And then David asked, have any of these installations utilized in-ground loops to supplement heating and cooling? And Roger, if you could talk about the Aspinall installation.
Sure. So for that particular project, we did have a 32-well ground source heat exchanger. So instead of having a cooling tower and boiler to condition that condenser water loop, it's really the ground that's acting as a thermal flywheel. In this particular project, we did have a fluid cooler just to allow for load balancing so the heat exchanger or the ground doesn't excessively heat up over time. So that's more of a ground source application, while water source VRF can be used either with ground source or a traditional boiler cooling tower configuration.
Thanks. And then Richard asked, what consideration is given to ASHRAE 15 and 34 designation and safety classification of refrigerants on the installation of VRF system with associated refrigerant piping throughout the occupied spaces. I think, Joe, you talked about that a little bit. I don't know if there's anything more we can add to provide for that question.
This is Roger. What's very common is using the dedicated outside air system ductwork network as a way to provide interconnectivity between smaller rooms so that if there is a refrigerant leak, the computation can be over a larger volume to stay within the ASHRAE 15 limits for acceptable safety. But it's something that has to be reviewed and actually calculated for these projects. Make sure everyone's kind of aware of what the actual approach is to maintain compliance with those standards.
Hey, this is Joe, Roger. To tack on to that, I think as owners we need to make sure that it's happening, that calculation is made and we have all the information. Because think about when we want to add on to the system in the future, we're going to want to know not only what was designed, but also what was installed. Did they put more refrigerant lines in, for example, and is that still compliant? So that when we go and add more systems, we can take all that information, hand it over to the next designer, because otherwise they're going to have to start from scratch.
Thanks. Richard asks, I don't think in any of our presentation today we saw instances of leak detection systems and alarm systems, but the question is, do you have to monitor for refrigerant leaks and provide alarms and mitigation in case of refrigerant leak? And so I'm wondering if there are any thresholds where a requirement for those things to kick in. You know, size of installation or volume of refrigerant or anything like that. I take silence as no. Okay, David asks, any problems encountered concerning piping or pumping refrigerant extended distances and elevations?
This is Roger. You definitely still have to be pretty careful with refrigerant piping distances. The good thing about these systems is they do allow for quite an extended amount of piping length, but it is definitely not unlimited. Sometimes there seems to be a perception that you can cover a very large building with without those limitations. And there is a difference in performance depending on the relationship of the condensing unit in terms of elevation to where your fan cooling units are located. But it's one thing that has to be reviewed fairly early on. A lot of the performance calculations for the equipment are actually done by the manufacturer. So I think that was alluded to early on in this presentation, that it's not something the design engineer can figure out on their own necessarily, that final limitation. You really have to, for a particular vendor, have them review the layout, where branch controllers are located, where the fan cooling units are located.
Okay, thank you. And then Opie asks, what are some of the typical refrigerants used by these systems and what are the costs? Are they proprietary or are they widely available?
So most of these systems use R410A, which is widely used. It's one of the most common refrigerants. It is I'm going to get it, an HFC. So there is kind of a move to address global warming potential refrigerants. I'm actually not sure what the latest or next generation of refrigerants that might be used for these systems are, but it's definitely something I'm starting to hear discussed a bit more in the industry as there's more demand to use fairly larger quantities of refrigerant, that some alternatives may need to be considered in the mid or longer term. But at least as it stands now, the refrigerants are widely available.
Okay, thanks. And then Brian asks, these systems operate like a multi-stage based on load, question mark?
They do. Typically, there is it's an inverter-driven compressor, but as I mentioned for the Aspinall, it actually operates in multi-steps, and if you have two compressors with one condensing unit, there's quite a lot of internal management of which compressor is running. Not something that you can directly control, but they're really optimizing its performance to make sure they have proper oil return, that the system's performing as efficiently as possible. It is a system that is, as we've mentioned, a black box, but in some ways it's good that there's not some external influence that can in fact impact the efficiency of performance.
Thank you. And here's a question. We are seeing many more cooling days and very high temperature days in the California Bay Area compared to just 10 years ago. We have an opportunity to do VRF at a smaller building, about 10,000 square feet. Would this make sense for this application? We're also retrofitting the building envelope for seismic and adding insulation, new windows, etc. Thanks. I don't know if you can answer the question with that, with level of information, but anyone have a thought on that?
This is Roger. That size of building is actually a reasonable application for VRF. One consideration is just how much individual zone control you need, because if it's just like one large space, that's 10,000 square feet. You know, using a separate type of unitary system, a rooftop unit, may still actually be more cost effective, but really if you have a lot of individual spaces across that 10,000 square feet, a VRF system can provide a lot of flexibility for providing thermal comfort efficiently.
Thank you. And then Clifford asks, how are you handling the warranty and after warranty support of the system? It sounds like you're going directly to the manufacturer. Is that a pretty fair statement?
Yes.
Yeah, and being proprietary and black boxes, it seems like that's the major route. And then one last question. And it says, are you going to speak more, or can you speak more about the separate provision of neutral, quote unquote, outdoor air? Any discussion, or can you share any more about providing outdoor air for these systems?
I can speak on behalf of
this is Ann, and
we have, oh, go ahead, sorry.
No, that's okay. This is Ann. I was just going to say we had mentioned the fact that sometimes if it's a renovation, if there's existing ductwork, people will go ahead and use that for the outside air ductwork. Again, you do need outside air. There are projects, and I'm glad to defer to Roger to talking about whether it's a DOAS system or how they have addressed that.
So for ASMO, we have a single dedicated outside air unit that provides generally neutral temperature air. Depending on your climate, you may sometimes want that dedicated outside air system to provide some more dehumidification. I think the good thing about VRF compared to, let's say, a sensible only cooling system like radiant cooling or use of active chill beams, the VRF fan coil units can actually handle some dehumidification still. So it's not a system that needs to operate totally non-condensing. So you can do some dehumidification to a kind of neutral condition at your DOAS, and still, for some climates, does rely on your VRF to do the balance. So there is some inherent flexibility in that. For ASMO, we had ventilation air ducted to mixing boxes for sealing ducted fan coil units.
Thank you, and thank you everyone for your contribution to the Q&A. I think, Andrea, that's the end of the Q&A.
Great, thank you. Thanks for all those great questions, and thanks for those really interesting presentations. So as we mentioned, if you want to receive continuing education credit, please complete the survey that you should receive within about 15 minutes. Today's webinar offers, I see that this is a typo, it offers 1.5 learning units for attending. And if you don't receive the post-webinar survey, please contact Michael Hobson. And with that, thank you all very much, and we look forward to seeing you back in September. Thanks again.